Hey guys, Christian Moseley here. I'm the group reporter for Group 1, and today I'll be talking about the results for the gas turbine and jet engine lab. So, first off, a little general lab overview. Uh, the lab was supposed to teach us about gas turbines and jet engines and how they work. And so, the best way to model them is with the Brayton cycle. And the ideal cycle includes an isentropic compression, an isobaric combustion, followed by an isentropic expansion, and then an isobaric heat rejection. So that compression is going to come from the compressor and the expansion from the turbine. And a key thing to note is that the turbine drives the compressor, so we will lose a little bit of work from that. And then on the right here, we have a diagram of what our system looked like. And at the end, we had a second turbine, which drives an electrical alternator, and that gives us power. So another thing to note is what kind of fuel we are using. We need to know. And so for this lab, it was kerosene, which has a density of about 815 kilograms per cubic meter, and the energy content of it is about 46.4 megajoules per kilogram. Another thing to note is the barometric or atmospheric pressure. We will need to know this because all the measurements we're taking for this are in gauge pressure. And so for Baton Rouge in April, the average is about 30.5 inches of mercury, and after our conversion, it becomes about 14.97 or 15 pounds per square inch. And then on the side right here, we have another look or diagram of our system, and it just shows the placements of where the sensors are and tells us where we will be getting our data from. All right, so first off, the compressor inlet. So our compressor inlet ranges at about 28 degrees Celsius. This graph seems a little off, or it seems like it fluctuates a lot, but it's really just a couple degrees. And 28 degrees is about 82 degrees Fahrenheit, which makes sense because this lab was done outside. So for our pressure, it starts off at just barely above zero. It's really 0.13 gauge, which is basically atmospheric pressure, and then it increases as our engine RPM increases. So for the compressor outlet, we can see on the left the temperature starts to increase almost linearly, except towards the end as our engine RPM increases, it increases a little higher, and that will cap out at about 130 degrees Celsius. And then for our compressor outlet pressure, we see an immediate increase. At the inlet, it was barely above atmospheric pressure, and now we're at about 5 psi higher. And we can see that as our engine RPM increases, the pressure increases as well. And at our max RPM, it's at about 21.7 psi gauge. So for our turbine inlet, this is right after combustion, so our temperature is going to be a lot higher because that kerosene is going to burn. We see that it starts off at about 500, and as we get to our max RPMs, it reaches a max of 765 degrees Celsius. Whoops, did not mean to do that. All right, so for our pressure for turbine 1 at the inlet, we see that it's roughly about the same as from the compressor outlet, which we would expect because it's isobaric. So for our turbine 1 outlet and turbine 2 inlet, they should be roughly the same, and our temperature is a little bit lower than previously. it maxes out at about 578 degrees Celsius, and our pressure also drops considerably. We only max out at about 3.1 PSI gauge. So for our turbine 2 outlet, we see another decrease in temperature. This time the temperature is still almost whoops. Sorry about that. All right, so for turbine 2 outlet, the temperature is pretty linear, and it caps out about 425 degrees Celsius at around max RPM. And the pressure is still dropping, and it maxes out at 0.6. So we're pretty much back to where we started at the inlet of the compressor. Okay, so for the fuel flow and the engine speed, the fuel flow maxes out at about 23.3 liters an hour, and the engine speed, our max RPM, gets to about 70,000, 70 and a quarter. One comparison, I would say generally most car engines redline at about 6,000 to 7,000 RPMs, and for a 737, their engines max RPMs are about 14 to 20,000. So this thing is going really fast. All right, so for our generator speed is what turning the alternator. The max RPMs is about 15,000, and then our max voltage gets to about 2.6, 2.7-ish. All right, and our generator continued. Our current gets to be at about a max 19.7 amps, and our powered generation is about 90 watts is the max. So this is data from a point I chose, which is at the peak engine speed, which is at that 70,250 RPMs. And this will be used to do performance analysis. And these are some of my references, and thanks.